Hey everybody, just from the ed puzzles that I've been watching, I'm getting kind of concerned that we don't actually understand this stuff as well as I thought. So let's go ahead and take a minute to go over these notes that I put into Google Classroom. All right, make sure if you do not understand this information, you ask me. All right, do not just put an I don't know answer in there. Okay, um, let's get started here. So, Aristotle on motion. So, Aristotle studied motion and divided it into two types of motion. All right, so one of them was natural motion, and the second one was violent motion. All right, so basically, like the up and down type of motion, objects would seek their natural resting places, right? So, heavy objects would fall and lighter objects would rise. Aristotle called this natural motion. All right, but violent motion was imposed motion with the result of a push or a pull. They didn't really have a name for force yet, so they just said if you were pushing it or if you were pulling it, you're imposing motion on that object. So that was violent motion. It was not natural, right? So Aristotle said natural and violent motion. Okay, moving forward, the common belief at that time, right, was that the earth was in the center of the universe and everything revolved around the earth. And that was the idea that because the earth was so big and massive, right, it just had to stay at rest. So this was the common belief that is an object was to be moved against its nature, right? If force must be involved, and if no force, then no motion, except in the vertical. Okay, so the proper state of objects was rest, right? So if you have this massive object like Earth, it must be at rest, right? So therefore, the Earth was at rest and all objects moved around it. Of course, we know this not to be true, but this is what they believed at the time. And this plants the idea that the Earth was too large to move and therefore must be at rest in the center of the universe. Then Copernicus came along. Okay, and Copernicus reasoned that the simplest way to interpret astronomical observations was to assume that Earth and the other planets move around the sun. Thank you, Copernicus, right? Because otherwise we might be a little confused in our physics class. But basically, he said that the sun was at the center and everything revolved around the sun. Then Galileo came along, right? Our main man Galileo, and his greatest contribution was he challenged the idea that a force was necessary to maintain motion. And this is a very challenging idea to even kind of wrap our minds around conceptually, right? Because intuitively we feel that, you kind of need a force to like keep things rolling, right? So this was like a very, very, challenging idea for people to understand even to this day, right? But Galileo proved this theory by creating what's known as a Galileo track. So Galileo argued that only when friction is present, a force is needed to keep an object moving, and he did so by building this track. So he had an initial position for this ball, he sent it down the track, and he concluded that the final position of that ball was at the exact same height as its initial position. Pretty crazy. And then he decided, okay, well, maybe it's just the slope, right? Because the slopes are the same, so we kind of expect it to end in the same position. So he changed up these slopes. So he put one as more steep, the less one as less steep, but the initial and the final position height were still around the same. So he said, well, there must be no friction present, right? Because if the initial position is the same as the final position, then it's not being slowed down at all. So then he said, okay, well, if there is no friction in this track and I just send it down the line, then it must continue on indefinitely if there's no friction present. So this is a exceptional idea from Galileo, and without this idea, we would, Newton would not have come up with his three laws. We probably would have never gotten to the moon. So thank you, Galileo, for saying and arguing these, friction present forces. All right. So again, Galileo on motion. So friction is the name given to the force that acts between materials that touch as they move past each other. And I know It's a very long definition, but basically, put your hands together right now. Rub them back and forth. Congratulations! You are feeling the effects of friction. Okay, so if you have, so friction is the name that is given to the force that acts between materials. So these are your materials, and the force that is acting between these two materials is known as friction, right? Because they are touching and they are moving past each other. So you are feeling the effects of friction, and friction is caused by the irregularities in the surfaces. So you have irregularities in your hand, there's irregularities within, road surfaces, grounds, all that kind of stuff, right? So when you have two objects that are touching and they are touching in such a way that they move past each other, and there's irregularities in the surface, then you know that friction is going to be involved there. So this is an example when there is not enough friction. So he doesn't slow down at all, so he just goes right into the mud. Okay, so when there's not enough friction involved, you don't get slowed down at all, so you continue in that motion until you stopped by a wall and land in the mud. All right, so Galileo stated that this tendency of moving body to keep moving, so just like in his Galileo track, it's natural, and that every material object resists change to its state of motion. So maybe just like you this morning, or even watching this video, right? You probably don't want to move. You're probably on your couch and you're like, nah, I don't feel like doing anything today, right? So Galileo would reason that that is natural, right? That only when you need to continue to change that motion do you need a force, right? So he called this natural state of resistance to your change in motion inertia. Right, so the property of a body to resist changes to its state of motion is called inertia. So if you do not want to change, right, your state of motion, so whether you're in motion or whether you're at rest, if you do not want to change that state of motion, that is called inertia. So that would be your resistance to change your state of motion. All right, so let's go over this picture really, really quick. So we have a baby in a car seat. It's like in the 1950s. This is one of like the first car seats. So they boosted it up so that the child could see past the windshield there. Okay, but basically, as we know, this child has inertia because it has mass. Right, so it has a resistance to change its motion. So if it's at rest right now, right, and they get in a car crash, well, they're going to feel the effects of the actual motion of the car. So they are going to keep on going. So basically, vintage car seats lets children see out the windshield before going through it. Oh, sad. All right, so Newton's law of inertia, or Newton's first law. This states an object continues in a state of rest or of uniform speed in a straight line, constant velocity, unless acted on by a non-zero net force. All right, so this is a super important law. This is Newton's first law, and it's also known as the law of inertia. So I know that was a long definition, so let's just break it down simpler. An object will remain at rest unless a non-zero net force acts on it, and an object will remain in motion unless a non-zero net force acts on it. We learned about net forces last unit, right? So a net force is the sum of, or the combination of, all of the forces acting on an object. So you will remain at rest or you will remain in motion until you have a non-zero net force act on you. And by non-zero, we just mean not zero. So you have to have a net force or an external force act on you in order to change your state of motion. Whether it's at rest or whether it's in motion, you need a force in order to change your state. Again, by non-zero net force, we mean an unbalanced force. So let's review types of forces that can act on objects. So you have contact and non-contact forces. So contact forces are interactions that occur between objects when they are touching. This could be like applied forces, spring forces, drag forces, frictional forces. The one and most important one that you're going to want to know is frictional forces and applied forces. So this would be an example of applied force. Again, you are touching them and applying a push to an object, which is a person here, and you are changing their state of motion. A bat and a ball would be an example of a applied force because you have that bat swinging around, hitting that ball, and changing the motion of that ball. You have a spring force here. Again, you have an object going into a spring and then the spring retracting and going into that object. We'll talk about spring forces later. A drag force, you've probably all heard of it before. In aeronautics, it's the mechanical force generated by a solid moving through a fluid, and a fluid in this case is air. Again, we're going to learn about this in later units. And the frictional forces. So we talked about this yesterday in class, but the frictional force in this case is that force that is opposing the motion of an object. So when you have two objects touching, that frictional force is that that change in that motion. It's opposing that motion, right? So you have the frictional forces of the feet on the ground and the tires on the ground as well. So non-contact forces are like magnetic forces, electric forces, and gravitational forces are what we know in this class as gravity, right? So gravity keeps us down, it keeps the earth round, it keeps everybody happy. So again, let's just jump back into Newton's first law. So unless an unbalanced force acts on an object at rest stays at rest, and an object in motion stays in motion. So let's look at this. So the fighter will remain in motion until an unbalanced force acts on it. So this fighter will remain in that rotational motion until either that fighter stops, so it applies a force to it, or throws the guy, right? Again, applying a force. And this couch potato, right? Probably like you this morning, will remain at rest until an unbalanced force acts on it. So whether they push themselves up or pull themselves out of bed, again, applying an unbalanced force in order to change that motion. So the pyramids, right, would be a balanced force, also a balanced force. The hockey puck in this scene of Mighty Ducks, you can go check it out on your own. This would be an example of an unbalanced force until it hits that wall or the glass or a person, right? Then it would be a balanced force. Unbalanced forces with skater wipeouts, again, you can check it out on your own. And then we say without air resistance, objects would drop at the same time. And you can check out this amazing video of the Falcon and an astronaut from the Falcon dropping a hammer and a feather at the same time on the moon. And you see them both hit the ground at the exact same time. Because we know in space there is no air resistance, so there's nothing to slow it down. So they are both dropping at the exact same rate. Right? So we know that they are both dropping at the same rate, so they're going to drop at the same time and land at the same time. So mass and inertia. Let's get to the good stuff. So the amount of inertia an object has depends on its mass. So roughly the amount of material present in the object. So I ask you, which one has more mass, 10 kilograms of gold or 10 kilograms of feathers? And you would say, Miss Brennan, they're the same, right? Because they both contain 10 kilograms. But what is different? Well, it's the volume. So the volume is the amount of space it takes up, right? So you can just visualize this. The feathers take up way more space than the bricks, right? So the mass is the amount of matter an object contains. So more mass equals more inertia. And again, inertia is that resistance to change in motion. So we said in this GIF, right, that car has a lot of mass, or it has a lot of inertia. So if it wants to stay at rest, it's going to stay at rest until an unbalanced force acts on it. And this unbalanced force is going to be gravity. Again, more mass equals more inertia or resistance to change its motion. So just like pulling that tablecloth with the dishes, this dog is pulling the sled with the child on it. The child has mass, so it wants to stay at rest until an unbalanced force of gravity forces it down. Same example here. Pretty crazy. So let's briefly talk about mass versus weight. So weight is that measure of gravitational attraction, and mass is a constant. So it's the amount of matter that you are made up with, right? So when I say find the force of attraction, you need to know that you need to find weight. How do you find weight? Well, you take W equals mg, where weight is W, m equals mass in kilograms, and g is the acceleration to gravity, 10 meters per second squared. I hope this helped. Let me know if you have any questions, and I'll see you all soon. Bye, all.